Welcome back to AI.Code.Cast, and you know what that means. It's time for another deep dive. Today, we're going to be looking at algorithms, specifically one called the repeated string match problem.
Yeah, this is a fun one. It's a classic, really tests how you think about strings and efficiency.
So imagine, right, that you've got two strings. Let's just call them A and B.
Okay, I'm with you.
And your goal, your mission, is to figure out, like, the least number of times, the absolute minimum you got to repeat A so that string B pops up inside. It's got to be a substring.
No, total sense. It's like you're trying to build a bigger string out of A, and B has got to fit neatly in there somewhere.
Okay, perfect. So let's say, just for example, A is Abe, just those two letters, and then B is Bubba.
All right, ab and babab. Got it.
So how many times would we need to repeat ab to make B that babab fit inside?
Let's see. Ab once, that's just ab, right. Twice is abob, and then that we do it 3 times. Aha. We get bob. That's where bob fits right in.
Exactly.
Yeah.
3 times is the magic number.
Yeah.
It's not just about fitting it in. It's got to be that smallest number of repeats, the most efficient way. Now, I don't know about you, but if I was, like, in a coding challenge and I saw this problem, I'd probably just start repeating A like crazy over and over and check if B fits each time.
Yeah, that's the instinct, isn't it? Just brute force it. Try every possibility until something works.
Right. But I have a feeling there's got to be a smarter way, something more elegant than that.
Oh, you're absolutely right. The brute force way, it works, but it can be a real drag, especially if you're dealing with long strings. Imagine repeating something 1,000 times just to check. Your computer would be like, whoa, hold on a second.
Yeah, it would probably melt. So where do we even start if we want to be smarter about this? What's the first thing to think about?
Okay, well, think about it. If the repeated A, even after all that repeating, is shorter than B, B can't possibly fit.
Oh, that's so obvious when you say it like that. It's like you can't fit a big blanket into a tiny suitcase.
Exactly. So step 1, before we even start repeating like crazy, we got to figure out how many times do we need to repeat A just to make it at least as long as B.
Right, so we're setting a minimum starting point based on the lengths. Okay, I'm with you.
Yeah.
So we figure out that number, the minimum repeats to make A at least as long as B, then what? Do we check if B fits into that length of A?
Well, you're close, but there's a little catch. Think back to our example Abe and Babab. We needed 3 repeats of Abe to make D fit. But what if we only repeated it twice?
So we'd have Abab.
Right. Babab is longer than that Abab, but it fits perfectly into Ababab because we have that extra ab at the end, kind of giving it room to breathe.
Ah, I see. So even if we calculate the minimum repeats based on length, we got to check 2 scenarios just to be safe.
You got it. One with that minimum number and then another with like 1 extra repetition just in case.
Okay, that covers our bases. It's like a safety net, right?
Yeah.
We've narrowed it down from potentially infinite repeats to just 2 crucial checks. Now, how do we actually do those checks? Like, how do we see if B exists inside those specific repeated A strings?
Let me ask you this. What are some of our tools when we're playing around with strings? Like, what can we use to see if one string is hiding inside another?
Is there some kind of built-in function for that? I'm thinking about, like, the find function, right? The one that lets you check if one string is inside another one.
Ding, ding, ding. You hit the nail on the head. Instead of building the whole repeated string first and then searching, we can use find strategically.
I like the sound of that. Strategically is good. So we take our first potential repeated A, use find to see if B is tucked in there, and if not, we move to the second potential length, the one with the extra repetition.
Boom. Exactly. No wasted effort, no building giant strings we don't need. We're working smarter, not harder.
I like it. But wouldn't we still have to build at least part of that repeated A to use with find? So, like, how much of it do we actually need to build before we start searching with find?
That's a great question. It comes down to understanding how find works. Remember, we're looking for the first time B shows up in A. That means if B is there at all, it's got to start within the first length of A.
Okay, yeah, I see that. So its starting point has to be in that initial part of A. But what if, like, it spills over? What if B starts in the first A, but needs a bit more space to fit completely, like it goes into the next repetition? Wouldn't we miss that if we only built one length of A to search?
You're catching on. That's exactly why we check those 2 lengths, remember?
Oh, right. The first one, the minimum based on lengths, covers the scenario where B fits nicely within that chunk. And then that second length, the one with the extra repetition, that's our backup to catch those spillover situations.
Precisely. We're making sure we don't miss anything. So we use find to check both, And boom, if we find B in either of them, we know we've got the minimum number of repetitions.
This is making a lot of sense. Way more efficient than just brute forcing it. Now, I'm just curious, are there any other ways to do this? Maybe even more efficiently?
You're always looking for the cutting edge, huh? Always pushing for that optimization. You know, there are actually some really sophisticated algorithms specifically designed for super fast string searching. Rabin-Karp and Knuth-Morris-Pratt.
Wow, those names sound pretty intense. Definitely want to hear more about those.
Yeah, they're powerhouses, real heavy hitters in the algorithm world. But before we get into those, maybe we should make sure everyone's comfortable with what we've covered so far. Any common mistakes people make with this find approach?
Yeah, good point. Got to watch out for those pitfalls.
Well, one big one is forgetting to check that second potential length. You know, the one with the extra repetition. B might need that extra space to fit, and if you don't check, you could miss the solution.
Right, overlooking that second check would be a pain. What else should people watch out for?
Let's see. Another common one is messing up that initial calculation. The minimum repetitions needed to make A at least as long as B. If you get that wrong, your whole search is going to be off track.
Okay, so double check those calculations and make sure you're testing both lengths with find. Great tips. I'm super curious about these Rabin-Karp and Knuth-Morris-Pratt algorithms now. They sound like they could take this whole string matching thing to a whole new level.
Oh, they definitely can. They're game changers for sure. But maybe we should take a quick pause here. When we come back, we'll dive into the fascinating world of Rabin-Karp and KMP, and you'll see how they can make even the toughest string matching problems feel like a walk in the park.
Sounds good. We'll be back in just a bit.
All right, see you soon.
And we're back with AI.Code.Cast, continuing our deep dive into the repeated string match problem. Before the break, we talked about the find approach, which is already pretty clever, but you mentioned some even faster algorithms, Rabin-Karp and Knuth-Morris-Pratt. I'm ready to have my mind blown.
All right, get ready for some serious string matching firepower. First up, Rabin-Karp. Imagine, right, you've got a massive library, like tons and tons of books, and you're looking for a specific sentence.
Oh man, that sounds like a librarian's worst nightmare. I'd be lost in those stacks forever.
Exactly. Rabin-Karp is like having a magic librarian who can instantly scan every single sentence in every book and sort them based on a special code, kind of like giving each sentence a unique fingerprint.
So instead of comparing whole sentences, which could take ages, we're comparing these codes. That sounds way faster.
You got it. This magical code, it's called a hash. We use a fancy formula that takes into account the letters in the sentence, and boom, it spits out this hash. If the hashes don't match, we know the sentences are different. But if they do match, we take a closer look just to be absolutely sure.
Wait, so there's a chance the codes could match, even if the sentences are different? That sounds kind of risky.
Yeah, it's called a hash collision. It's like two different people having the same birthday. It's rare, but it can happen. That's why we always double check if the hashes match, just to be super careful.
Makes sense. So Rabin-Karp uses hashing to speed things up. What about Knuth-Morris-Pratt, or KMP? What's its superpower?
KMP is like a super sleuth, a detective. It analyzes the pattern we're searching for, remember, that's our string B, and looks for clues that can help us search smarter, not harder.
Clues? Like, what kind of clues are we talking about here? I'm intrigued.
Let's say you're searching for the word banana in a huge text file. KMP is going to notice that banana has that nay sequence twice.
Oh, so it's looking for repeating patterns within the string itself. Clever.
Exactly. It uses this info to create a special table, like a cheat sheet, that guides our search. Think of it like a roadmap that tells us where to jump ahead in the text if we hit a mismatch, instead of starting back at square one every time.
Okay, so we're not wasting time backtracking over and over. We're being strategic about it. But how does this actually work in practice? Can you give me a simple example just to see the magic in action?
Sure. Let's say A is ABCD, nice and simple, and B is CDAB-DAB.
So our mission is to find the minimum times we need to repeat ABCD to fit CDAB-DAB inside.
Got it.
Now, with KMP, step one is to build that special table based on the patterns in B. It's a bit complex to explain right now how we build it, but trust me, it's some seriously clever stuff.
All right, I'll take your word for it. So we've got our table, our roadmap. Now what?
Now we start comparing the characters of B with the repeated A. We begin by comparing C from B with A from A. Nope, no match. Then we compare C with B, still no match. We keep moving along A until, bam, we find a match.
When we compare the C from B with the C from A.
Bingo. Now the next character in B is D, and the next one in A is also D, another match. And we keep going like this, comparing them one by one. Okay, but what if we hit a mismatch? Like, what if the next letter in B was X instead of A? What happens then?
That's where our KMP table, our roadmap, comes in clutch. Instead of going back to the beginning of A and starting over, the table tells us exactly where to jump ahead in A based on that mismatch. It's like skipping ahead a few chapters in the book based on a clue.
So we're cutting out all the unnecessary comparisons, being super efficient. I love it. So KMP is all about using the patterns within B to avoid wasting time.
Exactly. It's all about minimizing wasted effort, only making comparisons that are absolutely essential thanks to that clever table.
Okay, this KMP algorithm is truly impressive. I can see why it's such a big deal in the world of string matching. So we've got Rabin-Karp using hashing for speed and KMP using pattern analysis to guide the search. They both sound incredibly powerful. But how do we choose? Yeah, if I'm in a coding interview and I got to solve this problem, how do I know which one will impress the interviewer the most?
Well, like with any tool, it really depends on the job you're trying to do. Rabin-Karp and KMP both have their strengths and weaknesses.
Okay, so what are the trade-offs? Lay it on me.
Rabin-Karp is generally easier to understand and code up. But remember those hash collisions we talked about? If you're in a situation where those are likely, Rabin-Karp could give you the wrong answer.
So those collisions can be a bit of a wild card. What about KMP? What are its pros and cons?
KMP is super reliable. It doesn't care about hash collisions because it doesn't use hashing at all. But building that KMP table, that roadmap, it's definitely more complex, requires a deeper understanding of how patterns work.
So if I need something quick and usually pretty fast, Rabin-Karp might be the way to go. But if I need absolute accuracy, even if it takes a bit more brain power to set up, KMP is the champ.
You nailed it. It's all about choosing the right tool for the job. Sometimes the best way to decide is to just try both and see which one works best in your specific situation.
This has been an incredible journey so far. We started with this brute force approach, and now we're talking about these super smart, efficient algorithms. It's amazing what a bit of clever thinking can do.
Totally. And this is just scratching the surface when it comes to string algorithms. There's a whole world of techniques out there, each with its own strengths and uses. It's an amazing area of computer science.
Okay, before we go completely down the rabbit hole of algorithms, let's bring it back to our repeated string match problem. We've got all these tools now, but is there anything else we should think about when we're building our solutions?
One thing to remember is that these algorithms are usually described in pseudocode. That's a way of representing the logic of the algorithm without getting bogged down in the specific rules of a particular programming language.
Right, pseudocode is like the blueprint, the plan. It helps us understand the steps without worrying about all the picky syntax stuff. So if we were to write pseudocode for that find approach we talked about, what would that look like?
Well, first we'd calculate those minimum repetitions, based on the lengths of A and B. Then we'd make two versions of the repeated A, one with the minimum repetitions and another with just one extra just in case.
Okay, so we've got our two possibilities ready to be searched. What happens next?
We'd use our trusty find function to check if B is hanging out in either of those repeated A strings. If we find a match, great. We return the number of repetitions we used to build that string. If we don't find a match in either, then we know B can't be made by repeating A, so we return mash 1, kind of like saying, nope, not possible.
That's a pretty clear way to lay it out. We're basically just taking the steps we talked about and putting them into a more official format. Now, what about Rabin-Karp? How would we write that up in pseudocode?
For Rabin-Karp, we'd start by figuring out the hash of B, that special code. Then we'd go through the repeated A, calculating the hash of every substring that's the same length as B.
So we're like sliding a window along the repeated A, and that window is the same size as B, right? And we're hashing each window as we go.
Exactly. For each window, we check its hash against the hash of B. If they match, we take a closer look, compare them character by character just to be super sure. If it's a real match, we're done. If not, we keep sliding that window and comparing those hashes.
Way faster than comparing whole strings every time, that's for sure. Those hashes are like our little shortcut.
They are. And the cool thing about pseudocode is that we can focus on the big picture, the core logic of the algorithm, without getting lost in the little details of a specific programming language.
I see that. It's all about getting the concept across clearly. Now, what about KMP? What would that look like in pseudocode?
With KMP, the pseudocode would involve building that special table we talked about, the one that acts as our roadmap. Once we have that table, we'd go through the repeated A comparing characters with B.
And if we hit a snag, a mismatch, We consult the KMP table, which tells us exactly where to jump ahead in A.
You got it. No more backtracking like we're lost in a maze. That table keeps us moving efficiently through the repeated A.
Man, these algorithms are seriously impressive. So much cleverness goes into optimizing something that seems so simple on the surface.
I know, right? It's a testament to the power of algorithms, computational thinking. By breaking down a problem into smaller pieces and applying the right techniques, we can solve these really complex challenges with amazing speed and efficiency. It's what makes computer science so fascinating.
This deep dive has been an amazing adventure into the world of string algorithms. We've covered so much ground, from that basic brute force method to these mind-blowing Rabin-Karp and KMP algorithms.
It's been a wild ride. And remember, we've only just scratched the surface. There are so many more algorithms out there waiting to be discovered and used to tackle all sorts of incredible problems. It's a journey that never ends, always something new to learn.
Okay, before we get too carried away with all the amazing algorithms out there, let's bring it back to our repeated string match problem. Now that we have all these tools in our toolbox, is there anything else we need to keep in mind when we're building our solutions?
It's funny, sometimes the simplest things can trip us up. One thing to remember is that these algorithms are often described in pseudocode. It's a way of representing the logic of the algorithm without getting bogged down in the specifics of a particular programming language.
Right, pseudocode is like a blueprint or a plan. It helps us understand the steps involved without worrying about all those pesky syntax details.
Exactly. It's like getting the big picture first before diving into the nitty-gritty. So if we were to write pseudocode for that find approach we talked about earlier, what would that look like?
Well, we'd start by calculating those minimum repetitions needed based on the lengths of A and B, and then we'd create those two versions of the repeated A string, one with the minimum repetitions and the other with just one extra, just to be safe.
Perfect. So we have our two possible strings ready to be searched. Now what?
Then we'd use that trusty find function to check if B is hiding in either of those repeated A strings. If we find a match, we return the number of repetitions we used to build that string. And if we don't find a match in either one, well, then we know B can't be made by repeating A, so we return 1 = 1, kind of like saying, nope, not possible.
That's a pretty clear way to lay it out. We're essentially taking the steps we discussed earlier and putting them into a more formal, structured format. What about Rabin-Karp? How would we represent that in pseudocode?
All right, so for Rabin-Karp, we'd start by calculating the hash of B, that special code we talked about, and then we'd go through the repeated A, calculating the hash of each substring that's the same length as B. It's like we're sliding a window along the repeated A, and that window is the same size as B.
You got it. For each window, we compare its hash to the hash of B. If they match, we take a closer look, compare them character by character just to be super sure. If it's a real match, we're done. If not, we keep sliding that window and comparing those hashes.
Makes sense. It's way faster than comparing whole strings every time. Those hash codes are like our little shortcuts. Now, what about KMP? How would we approach that in pseudocode?
For KMP, we'd focus on building that special table, the one that acts as our roadmap. Once we have that table, we'd go through the repeated A, comparing characters with B.
And if we hit a mismatch, we consult our trusty KMP table to tell us where to jump ahead in A. Right. No more getting lost in the maze of characters.
Exactly. No more backtracking like we're lost in a maze. That table keeps us moving efficiently through the repeated A. It's amazing how much thought and cleverness goes into optimizing something that seems so simple on the surface.
I know. It's a testament to the power of algorithms, computational thinking. By breaking down a problem into smaller pieces and applying the right techniques, we can solve these complex challenges with incredible speed and efficiency.
It's what makes computer science so fascinating. This deep dive has been an amazing adventure into the world of string algorithms. We've covered so much, from that basic brute force approach to the mind-blowing efficiency of Rabin-Karp and KMP.
Wow.
It's been a wild ride. And remember, we've only just scratched the surface. There are so many more algorithms out there waiting to be discovered and used to tackle all sorts of incredible problems. It's a journey that never ends, always something new to learn.
This has been an incredible deep dive. We started with a seemingly simple question: how many times do we need to repeat a string? And look where we ended up exploring this whole spectrum of solutions, from brute force to these mind-bendingly clever algorithms. It just shows you that in the world of coding, there's always more than one way to solve a problem.
And choosing the right tool for the job can make all the difference in the world. So to wrap things up, what would you say are the key takeaways for our listeners today?
Well, first, I think it's a reminder that even a problem that seems straightforward, like repeating a string, can have hidden depths. There's always more to discover if you dig a little deeper.
It's a good reminder to never settle for the first solution you find. Always look beyond the surface and explore different approaches. You never know what gems you might uncover.
And second, efficiency matters, especially when we're dealing with large data sets or complex tasks. Every millisecond counts.
Those fancy algorithms might seem intimidating at first, but they can be real game changers when it comes to performance.
It's like having a secret weapon in your coding arsenal.
Exactly. So keep learning, keep experimenting, and never be afraid to dive deep into those algorithms.
Who knows, maybe one of our listeners will come up with the next breakthrough in string matching.
That would be amazing. The future of algorithms is wide open, full of exciting possibilities.
Well, on that note of inspiration, we'll wrap up this deep dive. Thanks for joining us on this journey into the world of repeated string matching.
We hope you learned something new, expanded your coding toolkit, and maybe even sparked some ideas of your own.
Until next time, keep coding, keep exploring, and keep those algorithmic wheels turning.
And remember, there's always an elegant solution out there waiting to be discovered. It just goes to show, in coding, there's always more than one way to skin a cat, so to speak.
And finding the right tool, the right approach, can make all the difference in how efficient and elegant your code is.
Absolutely. So, wrapping things up, what would you say are the biggest takeaways for our listeners today?
Well, I think one big one is that even a seemingly simple problem, like repeating a string, can have a lot of depth to it. It's not always as straightforward as it looks.
Yeah, it's a good reminder to always look beneath the surface, explore different angles, try out different approaches. You never know what you might find.
And the second thing I'd say is that efficiency really matters,
Hmm.
especially when we're dealing with tons of data or these really complex tasks.
Right. Those fancy algorithms, they might seem a bit scary at first, but they can be absolute game changers when you need your code to run like lightning.
They're like secret weapons in your coding arsenal waiting to be unleashed.
Exactly. So, to all our listeners out there, keep learning, keep experimenting, and don't be afraid to dig into those algorithms.
Who knows? Maybe one of you will discover the next big breakthrough in string matching, some algorithm that's even smarter and faster than what we have today.
That would be incredible. There's so much potential out there, so much more to discover in the world of algorithms. It's an exciting time to be a coder.
Well, on that note of inspiration, I think it's time to wrap up this deep dive. Thanks to everyone for joining us on this adventure into the world of repeated string matching.
We hope you learned some new tricks, maybe expanded your coding toolbox a bit, and hopefully sparked some new ideas in your own projects.
Until next time, keep coding, keep exploring, and keep those algorithmic wheels turning.
See you in the next deep dive.